Hey everyone, welcome to the last ACM AI Advanced Workshop for this quarter. And today we're going to be talking about modern deep learning. So everything from efficient neural networks, this landscape of LLMs, generative models, and more. And as always, here's the link to the asset cluster where you can find all the previous workshops, recording slides, and code demos.
And the way today's workshop is going to work is it's going to be very similar to how sort of an ACM reading group would be run if some of y'all have been to one of those. So this gives you a feel of what 4 very short reading group will feel like. And if you are interested and you think this is a fun way to learn, you can come to reading groups in the future. That happens usually on Saturdays from 12 to 2 p.m. at Engineering 6 to 29.
Next one is this weekend.
Yes.
All right. So yeah, with that out of the way, let's get started, starting with mobile nets and other efficient networks. So everything we've talked about machine learning so far, it's great. Like, it's achieved so many great things, but there's a bit of a problem, which is it uses let's say, a huge amount of memory. So if this is fine, if you're Jeff Bezos, name any billionaire CEO in the world, you've got all the money that there is, no problem. But what if you just want to run it on your phone? Well, this is a bit of an issue. So the problem is machine learning has a large number of parameters. I think the latest ones have, what is it, billions, even trillions of parameters. So, and that requires a lot of memory to store and also to deploy. Also because the training, even if you have a lot of these GPUs, these GPUs are very power hungry, and so we wind up using a lot of energy to train them. And also, this means that because we consume all this electricity, this also has a high environmental impact. So that's another problem. And also, of course, it's very computationally expensive. Like it says, with these matrix operations, you need a lot of, it's a very highly computationally complex problem. And typically saying you need very high-end GPUs for.
Yeah. Oh, and one thing, we're going the whole thing. Another thing with really large models is also GPU VRAM. So who here has been playing with PyTorch in the past and gotten the out of memory error and that you can't go any further? We have one person who has encountered it. If you haven't encountered it before, then you're definitely going to start encountering it in projects as well. But basically, in order for machine learning models to be able to run on a GPU, it has to be almost like cache itself in some sort of RAM that is on the GPU. Does anyone here know where RAM is and what the purpose of that is? Anyone who doesn't know? Okay, cool. So it's like this temporary memory thing, right? It has to the GPU has to put the model somewhere, and the issue is as it's kind of passing, forwarding through a model or training the model in terms of backpropagation, that takes up a lot of VRAM. And because VRAM is supposed to be very, very fast and it's directly in the GPU, a GPU, say, with 24 gigs of VRAM can cost upwards of can start at $1,000. And you want to go to a GPU with 48 gigs of VRAM, you're talking about server-side GPUs that start at $6,000 a thing. So VRAM is a very, very, very scarce resource, and one of the main problems nowadays with being able to run and train larger models. And you can also see how this can translate to, hey, if you want to deploy these models on our phones, which don't have a lot of VRAM in its tiny little GPU, we sometimes, it's not even it's too slow to run, it's we can't even run the model, right? Because it literally just will not fit on the GPUs on our phones. And this, what we're going to introduce today is kind of some solutions on trying to mitigate that. We have a model, how can we make it smaller so that we can put it on more, in more efficient scenarios? Yeah,
so we're actually, one of the examples we're going to look at today is an example of a CNN. So we talked about CNNs in an earlier workshop. I don't remember which one, but it's in the asset cluster. If you want to look at that. But just for a recap, we take an input as an image, and then we apply a convolution, which is basically we run a filter through it, and then we apply pooling to extract the most important features, and then sometimes we'll do multiple convolutions, and then we move that feature map into our fully connected layer, and then we apply softmax or some other activation function like ReLU to get our output predictions. So that's just a very fast overview of what's happening in a CNN. And so in a normal convolution, we have our input data, which is it's run through M channels, and it's DF by DF. So this is often like a couple hundred pixels. So that's just the size of the data that we feed in. And then we apply the convolution operation with each of these kernels, or filters. So K by K is the size of the kernel. And we just run that across each. And we have N of these, and then then when we do that, we get a dp by dp times n output. And so to do all of this requires n times dp squared times dk squared times m multiplications. But can we do better? Leo is going to talk about that now.
So yeah, we can do better for efficiency reasons. And one potential way is to use separable convolutions rather than typical normal convolutions. So, sorry for that spelling mistake. Separable convolutions help us decrease the number of multiplication operations of the CNN by sort of like separating the convolution operation over the kernel. So for example, if you have a 5 by 5 by 3 kernel, you separate it into 5 by 5 by 1 3 times, and then you use these kernels on the image, and then finally you'd have a pointwise convolution. So separable convolutions have two main parts. First, the depthwise convolution, and second is the pointwise convolution. So initially, for the depthwise convolution, what happens is, like I said before, you separate the kernel into its constituent parts. So in this case, suppose you have a 5 by 5 by 3 kernel, for an image, that's, let's say 80 by 80 by 3. You wanted to use the 5 by 5 by 3, you separate it into 3 5 by 5 by 1 kernels, so 3 5 by 5 by 1 tensor. And then you perform the convolution operation on those across the channel space, separate. So you take every single kernel, and then you have the convolution operation on each channel, right? And then comes the pointwise convolution operation, where we take our intermediate tensor. So rather than having before we had a typical convolutional layer where we'd have our tensor and we had our output tensor. Now there's an intermediate tensor. Then we take our intermediate tensor and we apply one convolution to it. So now we have the output. This intermediate tensor has n channels. In this case, it has 3 number of channels. So we take our one-dimensional convolution, and then we sort of like compress it into one feature map. And then we do this n number of times for the number of the feature maps that we want. And so this will help us reduce the number of operations that we need. And if anyone is wondering, why does this help us reduce the number of operations that we need? Why is it so effective? It's effective because we're only transforming the image once. So if you guys remember before, for convolution, say you have a kernel, you apply that kernel every if n is the number of feature outputs that you want, you have to apply it n times. So you have to transform the image n times. But in the case of separable convolutions, you don't have to transform it n times. You only have to transform it once, and then you apply the one-dimensional convolution n times to get those feature maps. So there's a reduction in the number of operations that you have, and specifically the reduction in the number of multiplication operations. And so this helps it out drastically. So this is very effective, especially in areas like, for example, mobile devices or embedded hardware, where you need quick speed and efficiency rather than going on.
And so kind of like very, very like vague, high level, like what's actually going on. If you're gonna think of each of these connections as like each of the channels in the middle of the convolutional neural network, a normal convolutional neural network basically does a dense connection, so like every single channel is connected to every single other channel. It's kind of like a fully connected layer, but in the channel dimension. But basically, what depth separable convolution does is it says, okay, instead of doing this like dense connection between every single channel, let's just make the first channel in the input match the first channel in the output, the second channel in the input match the second channel in the output, and so on and so forth. So this is like direct connection that is much sparser, right? There's much less connections, and most importantly, because it's much less connections, it's also much fewer in parameters, because you're not going to designing, one set of filters for every single kind of pair of the inputs and outputs of the filters. So you do this channel wise, and you basically like group them all together with a much smaller spatial much smaller point length convolution that actually groups the channels together. And because that convolution, so in this case the convolution, let's say we have 3 by 3, this part will be 3 by 3, but it's also much smaller, and this part will be 1 by 1, which only groups the channels together. So we're kind of separating the problem of, with a convolution, we gotta group nearby pixels together, right? And we gotta group near all the channels together. Instead of treating that entire problem as one big thing that we have to do with one huge matrix, we instead split it up, saying, first, let's make sure that the nearby pixels are being grouped together, and we don't care about the channels themselves. Then let's group the channels together, and we don't care about nearby pixels. So we're essentially kind of splitting up this process into 2 parts. And yes, there will be a loss of information in the process. Like you can see how this, just by having more parameters, this connection, the normal convolution connection, can represent more things than the definite separable convolution. However, when we train the model from scratch, if you go to the next slide, what they found is the performance hit is actually not that much. So that's the kind of general intuition behind definite separable convolutions. And a lot of times, you will have to either train the network from scratch. Like that's generally how it has to go. Like it's not like you can take an existing network and just make it smaller. This is like you have to start out with this architecture. Does that kind of make sense? Okay.
And if you guys are wondering, just judging from the image, there isn't that much of an accuracy gain when you compare it. In some cases, even the mobile net actually beats Google Net and so on in accuracy, which is kind of amazing, right? You guys might be wondering, why don't we just use a separable convolution for everything? There are differences when you have larger models, because technically, it's not like equivalent, right? Because you are losing some amount of information when you do use separable convolution. And so in some cases, the accuracy can decrease, but they're just fine in other cases. And this is an example, a common example of a streamlined convolutional neural network that uses separable convolutions. It's called MobileNet. If you guys want, you guys can Google it. There are a lot of cool papers on it online, and this is the architecture of MobileNet. When I first saw it, I was really confused. I'm still confused, but yeah, this is the architecture, and this is the accuracy of MobileNet with other common convolutional neural networks like GoogleNet and UGB. So yeah. And these are the number of parameters. As you see, million parameters. MobileNet compared to them, it's really not good, like 138 million parameters, which is kind of insane, right? So yeah, this is pretty cool. And like I said before, this is used mostly in mobile devices and embedded hardware. So things that you need to run it really quickly and really fast. And there are other aspects of MobileNet other than this that are also really interesting, but this is one of the key features. Another thing that we want to talk about is quantization. So in this case, if you guys have ever used PyTorch, specifically, you might have run into ears with float point values, right? So like 32-bit float values. Has anyone ever seen that while using PyTorch, or just in general? Do you guys know what a float is and so on? Integers are, right? Yeah. So you guys know they're just in C++, for example, you have integers, primitive data types, right? That store values in terms of ones and zeros at the hardware level. And in PyTorch, what is commonly used are 32-bit floats, right? And 32-bit floats are great, like your computer can handle them, but they do take up a large amount of storage. And the reason why we use 32-bit floats is because we want a high degree of accuracy and precision, right? And the key thing is that they're floats, so they require specialized operations to calculate like multiplication and addition and so on. Because floats and integers are different. The way floats are stored in the computer is totally different from the way ints are stored and the operations that occur for ints. So with regards to floats, this might be quite inefficient, right? If we have 32-bit floats in our program. So why don't we downscale it to make it more memory efficient. So what we do is we downscale it from 32 bits, maybe 16 or 8 bits, and then we can use those values in our neural network. This does result in a loss of accuracy a little bit because we have, your weights are a continuous value. And if you represent your weights as a 8-bit integer, in this case, it's an integer because we convert it to int now, rather than a 32-bit float, there is a loss in accuracy, but it's surprisingly not that much again. It's not as drastic as you would assume, and this can lead to better time efficiency and more optimality with regards to the amount of space used.
Yeah, and just for reference, usually when people are training neural networks, because when we're training neural networks, we're actually doing back propagation, right? And we can run into problems of like gradient vanishing, gradient explosion, like even just small degrees of that. Usually in those situations, we want to use 32-bit floats when we're actually training, because otherwise we run into gradients like explosions much more often, and like it basically becomes unusable. However, during inference, for most models, you can pretty much go from 32-bit floats to using 16-bit floats without like almost imperceptible like quality hits for both large language models and for generative models. And to go to 8-bit integers requires you to do a little bit of finagling. Like Qualcomm has a bunch of research on this, where basically they try to like group certain integers together and like do further fine-tuning within these 8-bit integer situations. And like also sometimes models, they will use mixed precision, where like certain layers are 32-bit floats and certain layers are 8-bit integers, to like kind of mix things up. So like maybe like the input and output layers, which is the most important for it to be precise, are like a full like 16-bit float, for example, but then the inside ones are much smaller. Like I know Qualcomm have managed to put like stable diffusion on 4-bit integers, which is absolutely insane. That is 2 to the power 4 with 16 possible values in total for one number, and they managed to fit a stable diffusion in that. It's a paper that you and I haven't really read too deep into it, but it's pretty cool. Like people have been doing a lot with quantization to try to make things runnable on smaller devices. Another plus is why we want to use these smaller ones is like a lot of the more modern NVIDIA GPUs, if you've heard like tensor cores, they have been advertising that. When they say tensor core, specifically they're referring to the ability to be able to do 16-bit float operations really, really fast. Which is why when you take like an existing large language models, and you have like an NVIDIA GPU or something, it will be much faster for you to run it on 16-bit floats, not just much faster, but also much more efficient in terms of VRAM. Because NVIDIA specifically went out their way to make this optimization for 16-bit floats.
So this is a great way to increase time efficiency. And another thing that you kind of want to plug in, neuromorphic computing. This is really, really cool. Check this out, guys. So, one big problem that you have with neural networks and large-scale neural network architecture is that they take a lot of memory, right? Because you need to train these neural networks continuously for days. Let's take, for example, Llama, right? You guys know like the open source model by Facebook. The open source model, like that's very similar to GPT, and it has a transformer model architecture. It takes around, I think, did it take them 10 days to train continuously, day and night, to train just that model, right? In ChatGPT, I don't think it took, I think it took months, if I'm correct, just to train it. And that's a very, very drastic amount of energy that's required just to train this neural network. So one potential other means is to use neuromorphic computing, which is a separate paradigm from the John von Neumann architecture that we use today. And like these are specialized chips just for this case. They're inspired by the brain, inspired by how like our brain has spiking activity rather than classic computer. Sure. This is the von Neumann architecture. You have your CPU, you have your storage, and you have your RAM. You can use it that way. Well, here information is stored within in terms of spikes, and rather than dealing with normal neural networks and for neuromorphic computing, you deal with spiking neural networks, which have again a totally different paradigm, and they're super, super cool. I'd encourage you guys to look into it. I think this is going to become really big in the future, and this is very time efficient because usually SNNs are sparsely connected, and because they're time based rather than compared to normal neural networks that aren't time based, because you have one activation after another, they're much more energy efficient. They're quite cool. check that out. So, and the landscape are generative vision.
Okay, so we're gonna now talk a little bit about generative vision and how it started and how we like the current landscape of it today. To give a little overview, we're gonna start from something called variational autoencoders. I'm gonna make our way to stable diffusion, which is kind of like or specifically latent diffusion, which is something which is kind of the predominant way that a lot of text to image generation is being done nowadays, what you guys think of as AI arts. So I guess before I get started, can I see a raise of hands? Who here has interacted with DALL-E 2 or stable diffusion or any sort of like text to image AI art generators before? Okay, we can see a good amounts. And if I were to give you a 1 minute summary of how these things work, right? How these models work. These models are based on a type of model called a diffusion model. And basically, to give a super duper high level overview of it, diffusion models maps noise to image iteratively. That's the main idea. It maps noise to image iteratively. Specifically, the way it does this is you put in some just randomly generated noise, and it's very easy for us to generate noise, right? Gaussian noise, stuff like that. It's very easy for us to generate that. You put it into the model, and what the model does is it takes in that image and it denoises that image just by a little bit. So we get a slightly less noisy image. You put it back in again. It denoises it slightly more. You put it in again, slightly more. Put it again, slightly more. And you repeat this iteratively until you get out a clean looking image. And these models, you can also condition them or basically inject information to them with, say, a text encoder. Do you guys remember what text encoders are? Vaguely from the, right? You're turning from words into vectors, right? So basically, you can put in a text prompt and it will be able to generate an image that actually fits the text prompt. So one of the ways to think about it is it's a denoiser that is so good that is able to denoise an image from absolutely pure noise. And that's the idea. But how did we get here, right? How do we get to this point? How do any of these moving components work? How do we even train a generator that's able to do a denoising like this? And that's what we're going to cover today. And before we do so, we need to take a step back and talk about some things that led up to diffusion models and some things that will be necessary for us to understand what it is. First thing, I want to talk about what is generative vision exactly. So most of what we have been learning in advanced track is what is called discriminative models, which is basically we're learning Py of X. What the hell does it mean? It means probability that image X is the label Y, right? Specifically, what we're essentially learning is we're putting in an image X, that's our input image, and it's going to outputs, and we have, say, 10 output label classes. Then what our model really is outputting is the probability that, let's say the label is dog. The probability of the image belongs to the class dog. And we have, say 10 of these probabilities for if we were to output to a 10 class classification model. And generative vision or generative modeling in general is something a little bit different. Instead of learning the probability that a certain input image belongs to a certain class, we're just trying to model the data itself. We're trying to learn the distribution of data itself. Because if we have managed to learn the data distribution, and we have some way, because if we have learned the distribution, we're able to sample from it. AKA, given the distribution, I want an example thing from the distribution. And what we have done is being able to generate new data from existing data, right? So specifically, we're learning the distribution of data set domain, right? And the data set is samples of the what's called image distribution. So the image distribution is not something that we can represent mathematically, because if we can use an equation to say, here is how to represent all possible images that humans will consider an image. What does that even mean, right? We can't really represent that. However, we can use a really big data set, of a bunch of images to represent samples from that distribution. And basically what our model is trying to do is say, okay, given these samples of distribution, I want to try to learn what this distribution exactly is. And then when we actually, sample from the model, we're able to get out new images. And we can also condition it with stuff, right? We can say, say in this case, maybe Y is a certain class. I want to generate an image of a dog, or Y is a text prompt. I want to generate an image of a text prompt. Then it becomes the distribution of images given that I have this input condition, say a text prompt. So that's what generative vision is, or generative modeling is. And we see that in recent research, we've been shifting from discriminative modeling to generative modeling. because again, like as I said, for example, with image classification, it has been largely quote unquote solved with image text, right? We talked about this. So that's why today a lot of our research is on generative modeling, or at least trying to understand generative modeling. So before we do this, specifically for generative vision, there's one thing that is very, very important. That is something called transposed convolution. So if you remember, convolution is what it does is it given an input image, it kind of is like it's this filter, we kind of drag this filter through an entire image and we do this, pairwise multiplication, we add them together, that's our output, right? And the point of convolution is that we're trying to reduce the dimensionality of the image. However, with generative imagery, a lot of times we're trying to increase the dimensionality of the image. Say we start from like a really, really small bit of noise, we want to kind of inflate that noise up to a final, the output that is equivalent to the final dimension of an image. And the way we do so is via something called transposed convolution, which is basically say, here's an example, right? Let's say we have input 1, 2, 3, 4, and we have 4 of our filters here. Basically, what we do is we say, okay, this kernel here, 2, 5, 6, -2. We're basically saying, let's multiply 1 to all these, and I'm just going to put it here on the top left-hand corner, right? And then 2, 5, 6, 2, I'm going to multiply with 2. I'm going to put it on the top, the right-hand corner. This is kind of our output stride. And by doing so, we're kind of almost like using this kernel as a template to kind of multiply all of our inputs. And by doing so, we're able to kind of inflate into a much bigger result. So does that kind of make sense? What's happening here? Yeah. So this is kind of what transposed convolutions are. They're kind of the opposites of what we consider as, normal convolutions. So we're basically almost like, upscaling the feature space by doing so. Then, with that in mind, I want to talk about the very, very first thing that we're going to be talking about today for generative vision, which is something called a variational autoencoder. So basically, first to talk about what a variational autoencoder is, we have to talk about what an autoencoder is in the first place. The point of an autoencoder is that we're trying to compress information and then reconstruct it. The way that it usually works is we have some sort of an encoder that takes in some input, usually say an image. And it basically compresses it down to like some really, really small vector. So like, we're going from a 1000 by 1000 image to say just like a 128 dimensional vector. We're compressing it to a 1028 dimensional vector. And our goal is we have this decoder, which is usually almost identical in architecture to the encoder, but just like with transposed convolutions instead. We're trying to reconstruct the original image. And when we're doing this, what we're basically doing is we're forcing the model to extract the most important information out into a much smaller dimensional vector, or even it doesn't have to be a vector. It can just be then a smaller version of the image, right? So we have this idea of compression and then reconstruction. That is the idea of autoencoders, and you may kind of start to see how this may be the basis for generative modeling, because it is really difficult for us to generate stuff from here directly. But if this is much smaller, maybe you can generate stuff from here instead and just only use the decoder to decode it. But here's the problem. When we're just training a normal autoencoder, we don't know what the distribution of this is. It is not guaranteed that this is the distribution that we can easily sample. This is not going to be like a nice normal distribution. It's going to be some really, really weird jank like vector that belongs somewhere that we can't really model. And this is where variational autoencoders come in. It uses this admittedly really complicated mapping that even like I've been staring at this for like over like 2-3 years now. I still cannot claim that I fully understand this. But basically what it tries to do is it tries to use this regularized loss to enforce that your kind of latent space in the middle, we call the middle part the latent space. The latent space in the middle follows roughly a normal distribution. And if it follows a normal distribution, we can sample from it, right? It's very easy to sample from the normal or Gaussian distribution. We know how to sample from the Gaussian distribution. And specifically, the way that it works is instead of learning this vector directly, what it does is it instead, when you pass an image, it tries to learn a mean and standard deviation of the image. And so during the reconstruction, it uses mean and standard deviation to generate a random vector and use that to reconstruct things. So basically, you're almost very high levelly intuitively trying to inject noise into the middle of this, so that the middle of this, because it starts from a normal distribution, strictly follows a normal distribution, right? So then to generate images, what we can do is say, give it a bunch of images from our data sets, learn and use that to find what our mean and a mean standard deviation is for these two. And then we just sample from this normal distribution to get our final outputs. Does that kind of make sense? So that is what a variational autoencoder is. And then, this is from the original paper, right? As you can see, the really amazing thing is, if say you generate a number from in this data set, for example, and it starts out to be the number 7, and you generate another number that's like, like the number 5, or like or 0 over here. The latent space inside is smooth. AKA, if you just interpolate between them, you can actually get this like smooth interpolation effect, which is very, very interesting. And even though back in the days, the generation results weren't particularly high quality or great, people got really excited by this because this is very, very exciting. And later, people developed this thing called VQVs, or vector quantized variational autoencoders, which is way more complicated. The main thing is that instead of learning mean and standard deviation, they learn this additional like dictionary of mean and standard deviations, like a bunch of embeddies, so you can generate much more diverse images. But like this is kind of the ceiling of where we can get with variational autoencoders, because we're trying to reconstruct the image directly, ultimately, and that's kind of difficult. So instead of trying to reconstruct the image directly, Goodfellow came out with the generative adversarial network. If I say the word Goodfellow like it's a big deal, he's a big deal because he's kind of a big deal. Who here has seen or been to like the AIX Cyber collab before? Okay, not a lot of people because it happens at the exact same time. What am I thinking? But the AIX Cyber collab, this quarter, we're actually basically implementing one of Goodfellow's papers in 2014 with something called fast gradient sign method, which is basically you're trying to attack a machine learning model. So say I give it a picture of a dog that very much looks like a dog to us, but the machine model very confidently thinks it's a cat, for example. But in 2015, he came out with this paper called generative adversarial nets. And it laid the groundwork. This is the first iteration of the generative adversarial network. And the way it works is it has 2 models. It's training 2 models concurrently. The first one is a generator. It generates images from easily sampleable noise. So usually you have some sort of like really low dimensional, 128 dimensional, for example, noise. And then you pass it through a generator. And the generator has a bunch of like, it transpose convolutions. You can start to see why transpose convolution is so important. And you have a discriminator, which has one job. It's trying to tell generated images apart from real dataset images. So it is basically a binary classifier. It gets an image and it says, is this image real or fake? And the goal is, during training, we give the generator some noise. It generates a fake image. This fake image will start out really, really bad. And then we pass this fake image along with a real image to the discriminator. And the discriminator basically tries to say which one's real, which one's fake. Obviously, in the real world, you would pass in a much bigger batch of fake images and much bigger batch of real images. You mix it together, and the discriminator has to tell it's a binary classification with batch size. But the point is, then we train both of these concurrently. And the idea is the generator will eventually, basically mathematically show this, the generator, the distribution output of generator will eventually slowly converge to the distribution of the data set, because this is the most optimal like equilibrium that it will reach. This is the minimum when we keep optimizing generator. So in the most ideal case, the generative adversarial network will perfectly model the data distribution. Put in simpler terms, what's happening here is basically the discriminator will get good at telling between fake images and real images. However, the generator, it will also get good at fooling the discriminator that this is a real image versus this is a fake image, right? So eventually, when the discriminator and the generator both get really good, if you just look at the generator, you have a generator that is able to fool a really good discriminator that this fake image is actually a real image, aka you have created an image generator that is able to maybe fool us as well. So real image is like an images we actually from data sets. So it's obviously to train all these models, we need some sort of source data set, right? Like this one's is MS, this one's just a bunch of bases, right? So, and fake images is images generated by the generator. Does that make sense? Yeah. So, yes.
Is it noise a fixed input or a spiral?
Depends on the architecture, but and the very first variant is just random every time. So every time you generate things, it's going to be noisy. Like basically every single time you generate an image, you just generate a random noise vector. Yeah. Does that make sense here? Okay. No, fake image looks just like a normal real image. So we're not at diffusion models yet. These are what came before diffusion models. Okay, yeah. Just to be clear, we're not at diffusion models yet. This is what came before diffusion models, right? Diffusion models around 2020. We're still around 2015 right now. Well, let's see. So this is the style GAN, which is like the most popular, one of the most popular, like generative adversarial network architectures, and it is behind this website called thispersondoesnotexist.com. The fun thing about this website is you can keep refreshing it, and just gives you a new image of a face every single time. Every single one of these are not a real person. They're generated by a generative adversarial network, specifically the style GAN. And they look real. They look really good, right? This is a very fun website. But like sometimes I'll just stare at this for hours. And I'm kidding. But this is the architecture behind it. It's a lot more complicated, and in the interest of time, I will skip this part, like style GAN. But the idea is that style GAN, it tries to disentangle the latent space itself, so you can do like fun, interpolations. But the point is, generative adversarial networks are really good because of this adversarial process. It's never trying to estimate the data distribution directly, right? We're never training it to be like, oh, the output has to be within an error of this input data. We're never asking it to do that. However, through the process of this adversarial loss, what we have actually let it to do is we're forcing it to learn this data distribution, because the only way for a generator to succeed is by learning the data distribution. Does that make sense? Obviously, the generative adversarial networks have a lot of pitfalls. Like, you do run into a lot of issues trying to train the network as well. Like, for example, something that you may run into, something called mode collapse, which is the generator figures out that the discriminator is really bad at distinguishing one specific type of image. It just keeps generating that same type of image repeatedly. Like, for example, like if generating pictures of faces, it may realize that generating a picture of a person with a red dots in this corner really screws up the discriminator, and the discriminator thinks that is a real image. Then it will just keep generating that. So like, generative adversarial networks, one of the downfalls of it, it's really unstable to train, because you have this adversarial loss where like you have to somehow balance the two losses so that they both learn at a very similar pace. There's been techniques to try to help us to train it in a more stable way. In fact, one of the tracks this quarter and next quarter as well in projects track is you're going to be training your own generative adversarial networks to generate emojis. It's very fun. It's kind of painful because you're going to keep running into these issues, but you'll learn a lot along the way. So that's generative adversarial networks. And kind of as a summary of what we have seen so far, like a lot of these seem like almost very unstable and jank. Like it's like a lot of these networks are like, okay, sure, I guess that works. It's like it's not something you would think at first glance, like, oh, that's how I'll generate an image, right? Like VAEs, and we don't have our regressive models here, but never caught on. And GANs, however, still, by the way, are amazing. I personally think it is one of the best pieces of research to ever come out in like the 2010s in machine learning. But the thing is, a lot of these models are actually very, very data set dependent, right? Whatever data set you put in, it's only going to be able to measure kind of approximate the distribution of that data set. It's not able to generate outside of the data set. And if you give it a very diverse data set, like ImageNet, where there's like 1,000 classes, it becomes very difficult for it to be able to generate all these images, because it's very unstable to train. There has been some exceptions, like the big GAN 2018 paper. GANs are actually pretty good. But a lot of these networks have a sort of like almost like upper limits. It's hard for us to go big. So how do we go big? Transitioning. Okay, anyway, so as I was saying, diffusion models are a denoiser that is so good that it generates an image from pure noise. And we're going to dig deeper into how it actually works now. So currently, we're still not doing text conditioning, right? We're going from noise to image. No text conditioning yet, because that comes a little bit later. But this is the first-ish work that showed that this is possible, aka this is going to maybe have the potential to beat generative adversarial networks. Because in the beginning of 2020 and 2019, 2020, if you come up with a way to beat generative adversarial networks at generating images, you've done a really big thing. And that's what Jonathan Ho from this paper and also Yang Song from a previous paper in 2019 have managed to do. And the key is this. Oh, by the way, in this case, like competitive results, low FID score. FID is back in the days what people used to, back in the days, they still use it today, like what they used to measure how well a model is able to generate images. specifically the FID score measures the difference between two distributions. So what you do is basically you say, okay, I have you have this really large image classification model, specifically the inception model, which is think like ResNet on steroids, right? You have this model called inception. You take the output vector that's right before the classification layer. If you remember me talking about a few sessions ago, how like you can just take second layer outputs and use them as embeddings. You take your input real images, your real data set images, you pass it in through that model, you get out a bunch of vectors. You take in all the generated images from your model, like say you generate 50,000 images, you pass it through the inception model, and you get out a bunch of vectors. Then you look at the distribution of these two vectors. The more similar these two distributions are, the lower the FID score. So basically what FID is measuring is how well is your model approximating the input data sets. And the reason why we want to use like an inception model is because we want to first pass it through a computer vision model so it can kind of like extract the necessary features. So if the features match, then they match, right? So that's basically what this is. That's what FID scores are. Any questions before I move on? Okay. So this, I know this is a lot, but I'm going to walk through everything very slowly as well. So the DDPM, or almost like the first variation of the diffusion model, is conditioned on something called T. And when we say conditional, meaning we're passing in this T value into the model as we're training, right? The model is dependent on what this T value is. Basically, in addition to the input image or input noised image, it also takes in T as an input. We have this T where when T equals 0, the image that we pass in has absolutely zero noise. And T equals to some big T, in this case T equals 1000, which is what they showed in the original paper, is pure noise. It's just, pure noise over here. And the idea is that as we show the model how to go from T to T minus 1, we keep showing it at all the different T's. How do you go from T to T minus 1? It is able to basically, given this T, be able to take a noise image and go from the noise T to slightly less noise at T minus 1. And then we do this iteratively. And by the end, we have a final output image. That's the idea. And to go into a little bit more details, we're actually going to look at how it is trained. This looks daunting, but I will break it down. So first, what we do is for every single iteration, we choose a random image from dataset, right? Say a random x0 from dataset. And we call it x0 because remember, 0 is no noise. A random image from dataset has no noise. Then we choose a random time step, right? Our range of time step in this case is 1 to 1000. We choose a random time from that. And then we also sample some random noise. So this is just some random noise that we will be adding to the image. And then here's where the important part comes in. First, we add the noise to the image based on this noise schedule alpha t, which is not terribly important. The point is that we have the scheduling of like how do we actually add noise. So first we add this noise to the image, multiplied by some constant in front. So we're kind of taking a linear combination of the two, right? So we have kind of took our noise, took our image, and we just added some noise to the image, right? That's the first step. The second step, the model, epsilon theta, in this case, usually in machine learning cases, when we see theta subscripted to a thing, that usually means this is a trainable thing of a model. The model is given our two inputs, our noise image and our current time step t, which represents how much noise we have added to the image, right? So the model takes these two things as an input, and it predicts, very crucially, the noise that was added. It does not predict the image itself. It does not predict what the image originally is, but instead, it predicts the noise that was added. And lastly, what we want to do is minimize the error between what the model has predicted as the noise that we added to the image versus the actual noise that we added to the image, because we sampled noise here. And that's how the diffusion model is trained. To recap, first, we choose a random image, and we choose a random time step, which represents the amount of noise we want to add to the image. And we generate some random noise as a sort of record to be like, hey, this is the noise we're going to add to the image. We first add this noise, the amount of noise to the image based on time step t. We pass that along with time step t itself into the model. And the model predicts the noise that we added to the image, and we're trying to minimize the actual noise we added to the image versus what the model predicts as the noise we added to the image. Does that make sense?
Yes.
Why don't we choose a random noise level instead of just going, because initially we're saying we start when there's like no noise and then we go back.
Yeah.
Why is it like distribution?
Right. So basically, what people found is that the best way to train is actually just to start with a bunch of different noise levels and just kind of go like, all right, here's what it looks like at t equals to 700. Here's what it looks like at t equals 50, and just keep doing this, and the model eventually learns everything. There are actually some like scheduling methods where they're like start with the slower t's and then slowly work your way to all the t's at once. Like there's a lot of different papers later that have tried to improve this training process. And specifically, like the reason why we have this like arrow situation was like, oh, you're adding noise and you're going backwards it's just because we're showing you the process of like, hey, we're like iteratively adding noise. The whole thing with iterative adding noise actually has some details in it that we won't cover today, but we will in the reading group. But this is the main idea that I wanted to take away with. Does this kind of make sense? Okay. So then, given that we have this model, how do we do inference, right? We have this model trained that is able to, when it takes in an image with t levels of noise, it is able to figure out what noise we have added to the image to get to that t levels of noise. How do we actually do inference? And the way we do it is like this. So we start with some Gaussian noise. We start with some randomly sampled noise, which is going to be at t equals 1000s. Then we do this iteratively. First, we actually predict the noise in x. T. So basically, we pass in the model in, we pass in t, and we say, okay, predict what the noise is. Then we want to subtract the predicted noise from our noised inputs to get a predicted denoised image. So basically, this is what the model kind of quote unquote thinks. This is what the denoised image should look like. And I think you can kind of see how when t is very, very big, this prediction is very awful because there's so much noise in the image. But when t gets small, this prediction gets pretty good, right? Because it becomes much easier for the model to separate the noise in the image. And then what we will do is we will add slightly less of our predicted noise back so we get a predicted x of t minus 1. So again, to reiterate, we first figure out, let the model predict what noise we added. We subtract the noise away from the original image to get what the model thinks the final image should be, which is probably a pretty terrible prediction in the beginning. However, to assist the model even further, we say, okay, you only did, well, we're just going to let you denoise just a little bit. So we're going to add back the predicted noise that we just subtracted, but we don't add all the way to the t levels of noise. We instead add to t minus 1 levels of noise. And we do this again and again and again. And you can kind of see how, because we have this freedom of how much noise we add back, instead of just doing t minus 1, we can actually do like t, we can actually just do like t minus delta of t, right? Because, oh, this actually delta of t, I should put this here. But instead of adding back, just t minus 1 amounts of noise, we can just do like t minus 50 amounts of noise. So instead of having to pass through the noise image through the model, say like 1,000 times, because we have 1,000 t's, we can say, oh, let's skip 20 every time. I'm going to have to do it 50 times now. And that's much faster. It's accelerated sampling. And I'm skipping over some details, but this is actually a development by a later paper. The original paper basically said we got to do it 1,000 times, and people were like, "All right, sure." But the later paper, literally like 4 months after the original paper, basically said, "Hey, we don't actually have to do that." And this is kind of the findings of the later paper. And you may be wondering why? What the fuck is this? Why is it random noise? We're not really going to talk about this today. The short answer is, what people have found later kind of is that when you inject noise into this process, it actually makes the prediction a little bit better because the model is able to kind of explore different paths a little more. You're kind of saying, oh, model we predicted, I don't believe you. I'm going to add in some noise myself, and you have to explore all the possible options. But again, we're going to talk about this more in detail in the reading group as well. So one of the ways that people have managed to figure out to like formulate all of this is it's just a differential equation, actually, which is that what the model is really doing is it is mapping from a normal distribution to an image distribution. And the process of iteratively calling the model and denoising is just us going, all right, we start from a normal distribution somewhere here. We're slowly tracing a path that hopefully will get us close to the data distribution, right? And you can kind of see how, like, the whole, like, injecting noise thing before, if we inject some noise here, it will make the path a lot more jagged. And maybe by making the path a lot more jagged, the model can explore more of the space as it's trying to go from the prior to the data, or go from a noise distribution to the image distribution. Because it can explore more paths and have more chance to correct itself. Because one of the things that I think the reasons why diffusion models work so well is because we're passing the image repeatedly back to itself. If it say screws up the prediction a little bit and there's some like weird artifact within the image, but when you pass the image back to itself, it can kind of go, oh wait, I screwed up there. Let me try to fix that real quick. It has a self-correction property to it, right? So this is why a lot of people are saying, oh, the diffusion process is just a probability flow ordinary differential equation. And yeah, it's just that. And basically, later some people actually develop a bunch of methods of like, oh, we don't have to, like, this sampling process is actually just the Euler sampler, by the way. You may learn this in Math 33B, and you can actually use second order solvers to do a bunch of things that people milked a bunch of papers out of it. But the point is, this is how most people look at diffusion models nowadays. It's just this kind of like differential equation. So again, we show the model how to map from data to noise, and by doing so, the model learns to map from noise to data. And that's the basis of how diffusion models work. Does that make sense before I move on? Okay, cool. And I want to talk about something real quickly, which is U-nets, because U-nets are actually like, we've been looking at this model and I've been kind of treating the model as just like a model. It's a black box. What exactly is it? It's a CNN, of course, but a very specific architecture of CNN, which is something called a U-net. Specifically, kind of similar to an autoencoder. What a U-net is it starts out with just a bunch of convolutions and kind of downsamples those convolutions to something that's much smaller, like usually like a vector or like some really, really small size. In this specific case of a diffusion model, it goes from like 64 to 64 to like 8 by 8 or something like that, right? So it downscales it and then it upscales it back. So it upscales it with transfer convolutions and it upscales it back, and it has these like long skip connections, kind of like super duper big ResNets. It has some self-attention layers, and use a sinusoidal embedding as T. We very briefly talked about this in the transformer workshop, but it's fine if you don't remember. The point is, the model is compressing the inputs to extract the most important information, and then use that said information to inflate the outputs. And that's kind of the architecture of the diffusion model itself. Okay, so then the question becomes, how exactly do we do text encoding, right? How do we do this text encoder thing? So the way we actually do text encoding is something called CLIP, which is a piece of research in 2021 from OpenAI. And it is very, very revolutionary. It has almost 10,000 citations by now. But the idea is this: how do we turn text prompts into vectors? We have very established solutions to that in the natural language processing space. It's just like, oh, we can like let a model predict where, how to, like what the next word is, or like predict, like we mask random words off, predict what those words are, and now we have a word embedding thing, right? But the issue is traditional text embeddings doesn't work because they don't contain visual information. You're only training on text data. Why would you expect that this text information is going to work for a model? So this is where CLIP comes in. It uses something called contrastive learning, which is we have a data set of text and image pairs. So usually captions and images themselves, right? And we're training two things jointly. We're training the image encoder and a text encoder. So we have a bunch of these text and image pairs, and we pass them, the text ones through the text encoder and the image ones through the image encoder. And our loss is twofold. We have two objectives. The first objective is the output embedding. So usually both of these output a vector that is exactly the same size. The output embeddings of the text and images that are in the same pair should be the same. That's the first objective. The second objective, the embedding of the text and image in different pairs should be different. So what this is basically saying is, if these text and images are pairs, then the output embedding they have should be the same. However, if a text and an image is not paired, their output should be different. And just by doing so, we're able to, and because we're trying to make sure that if they're in a pair, these embeddings are the same, we have essentially created a text encoder and an image encoder that maps to the same space. They map to the same embedding. And because the image encoder necessarily has to encode image information, and the corresponding text encoder of the caption for that image will map to the same embedding, suddenly we have a text encoder that contains image information, that contains visual information. Does that kind of make sense? Any questions before I move on? Yes.
We simply modify those two values extracted from the graph and the tax, or there are some like more complex computation there?
Oh, we basically just go like we calculate, I think, the cosine similarity between the two. Yeah. Okay. Then with that in mind, we get to latent diffusion models, which is how almost every single like large text to image models are implemented today. I'm skipping over some things in the middle, but the idea is first we use a first stage autoencoder to do diffusion in the latent space. So basically we take in, again, our training data set is a bunch of image and text pairs, right? We first just look at all the images. We look at all the images and we say, okay, I want to train a really, really big autoencoder that embeds this image into a smaller space that we don't really need it to be like a normal distribution in, and then we inflate it back to the original things. So we have this autoencoder that is basically able to compress specifically a 512 by 512 image to a 64 by 64 image, right? It's slightly smaller, has a few more channels, but it compresses it down. And then we basically train a diffusion model conditioned now on our text within the 64 by 64 latent space. So instead of training on the image, we trained on the autoencoder encoded version of the image. And so when the diffusion model, what the diffusion model outputs is actually a version of the image that is within the latent space. So all we have to do is put it through the decoder and we get a final image. And the reason we want to do this is because it is already very, very expensive to train a diffusion model on, say, the 64 by 64 resolution level. If you want to inflate it up even further, every single two times resolution up is exponentially larger in terms of the actual model number parameters we need. So basically, we're almost cheating by saying instead of training in the image space, we're training in the latent space of our encoder and decoder. And that is how stable diffusion works. In fact, LDMs is the framework or like the base method for which stable diffusion is trained by Stability AI later, and it has become the open source monster that has basically made a lot of generative AI research possible. And it's trained on Lion 5V, which is this like scraped internet image alt text pairs, which you can see how that has a lot of problems with copyright and stuff like that. But we don't have enough time to talk about this today. Does that make sense? How stable diffusion works and most image generators work nowadays? Okay, cool. Right. Okay. So yeah, what just happened is you basically saw a preview of the Saturday's reading group. We covered like 70% of that, 80% of that, 40% of that, and there's like 3 whole sections of like what people have been doing with diffusion models today, and just a little like preview of like what we're going to be talking about. Like, there's a lot of things we're going to be talking about. So if you want to learn more about diffusion models and also get another refresher of what I talked about in the beginning, because I did go through things very fast, come to reading group this Saturday. But let's move on to the next topic: introduction to reinforcement.
Hello, everyone. Okay, so the third topic out of the 4 topics we're going to be talking about today is reinforcement. So far all the models that we've talked about, right? They've had explicit training data and testing data, right? You have some training input, and then you're trying to match some sort of performance. So you get an accuracy measurement whenever you're trying to pass things through the model to determine how good your model is. Now, the thing is that this works really well if you have explicitly labeled data. But if you have a lot of real-world tasks, then this suddenly doesn't work quite so well, right? So if you think about, say, driving a car, for instance, right? You're not getting like feedback every single time you make the tiniest decision about whether it's the right decision or not, what the accuracy of that decision is, and so forth, right? If you turn the steering wheel one way or the other, if you accelerate some speed or the other, you don't get like instant real-world feedback that way, right? You just sort of get a general sense of, have you succeeded at this task, or have you, failed at the task and like crashed into a tree or something. So that is sort of the way that you motivate reinforcement learning, and why we might want a different paradigm for it as compared to standard machine learning. So whereas in standard machine learning, you have explicit label training data, with reinforcement learning, you collect data during training. So as you keep driving, right, you'll get exposure to some other situation. And then when you learn, you take a situation in, then you respond to it. Another assumption with supervised learning is that your training data is each sample you get in your training data is distinct from every other sample, right? So that means that you're not like influencing how you're learning based on things you've learned in the past. Everything is new each time you get a new sample. But that's not going to be the case. Again, I'll just use driving a car because it's easy. Like if you're driving, then every single sample you see is influenced by what came before. right? If you're driving through a field, for instance, then every single thing that you see subsequent in the field, right, is going to be dependent upon where in the field you've been driving. So your past decisions sort of stack up. And then the biggest difference, I think, as far as ML goes, is that for classic machine learning, you're just learning to predict y from x, whether that's a regression task where you're trying to predict what value y has, or whether it's a classification task where y is some sort of class you're trying to predict. But here, instead, what you're trying to do is you're trying to learn to maximize the reward function, where this reward function encapsulates how well you're doing your task. So that's just the very basic difference between reinforcement learning and standard ML. So in order to phrase things in terms of a reinforcement learning problem, I'll just say RL, is that you need to know these four things. You need to know your state space. This is all possible states that you could see, all possible states that your model could be in. Then you also need an action space, which tells you all the possible actions you can take, and it will take you from one state to another state. So if you're, say, if I'm standing over here, for example, right, there are a few actions I can take. I can take a step in this direction, or I can take a step in this direction. And those would be, I guess, one state and two possible actions. But now imagine like all possible states I could be in and all possible actions I could take in those states. Then next up, you've got your reward function. That tells you how desirable your current state is, how desirable your current model is. And then lastly, you've got your dynamics. And these are the environmental constraints that you have. Like, for example, if I'm walking, right, I can't like fly into the air. So the constraint here is that we're limited to 2 dimensions. Okay, so I've been talking a lot about like walking and driving and so on, but you can also apply reinforcement learning to a whole bunch of other things. This is an example of a board game, where state space is the state of your board, where all the pieces are. Then the action space is every single valid move that you can make. Your reward is win or lose. And your dynamics are just the game moves. So here again, one thing you'll see is that the reward is just 1 if you win, 0 if you lose. So it's not like every single action you take like will automatically get your reward, right? It's something that you get at the end of the game. So it's not like moment by moment updates. Okay, so now this looks pretty complicated, but all it is just a sort of graphical representation of what we've been talking about so far. So if you start off in this state, for example, and you see this as the observation from your environment, then perhaps if you see this observation, then you want to take this action, and that action is going to take you into this state. So if this is a type of graph that will reflect something called the Markov decision process, where there's a probability of transitioning from one state to another state and so on, and you basically reflect that with this graph. So every time you see a graph like this, you should just keep in mind the underlying format of what this means, which is given a state and an observation, you're going to take an action that's going to take you to another state, and so on. And each action has some probability associated with it. So if you have multiple possible actions, right, there's some probability that it takes one specific action that will land you in one specific state. Okay. So again, this is the sort of another way of looking at it, which is if you have an agent, this is your model, or maybe a person, who knows, we'll go into model. And then based on the current observation that the person's making and the policy that you've learned, so this would be the model, like the parameters that the model has learned, it will take an action, and then the action is going to affect the environment, and that's going to put you in another state. And then based on the reward associated with whatever action you just did and the state you're in now, you're going to update your policy so that you can maximize that reward function for the next time that you have to make a decision. Okay. So if you go back here, I said, based on this data, the policy the agent has learned, it will take an action. So just sort of delve into the weeds of what exactly that means is this thing. So the idea here is that if you have some probability that given a state and an action, you're going to enter another state. That's the probability of that happening. And then this is the reward associated with jumping into that state. So this would be the reward for entering that state plus And then this reflects the reward of all possible future actions you could take from that state. So you have the reward for entering the state plus the reward for all future actions you can take from that state. And that will equal the reward for entering that state with that action. So the idea here is hopefully that you're sort of encapsulating what we had before, but mathematically. That you have some reward for entering a new state. And that reward tells you how desirable that action was. And by extension, the policy that led you to take that action. Okay. Now, going back here, on the fourth part here where we said based on the reward associated with the current action, the agent will update its policy. So when we've talked about updating model parameters in the past, right, we've always talked about gradient descent. We've always talked about you take the derivative with respect to the weight and the bias and so on, and then you just sort of backpropagate through the model like that. But the problem with reinforcement learning is that doesn't work. And the reason it doesn't work is that in the real world, there are certain events that happen that you can't differentiate. You can't evaluate the rate of change. Like if you have something that happens really suddenly, like something just jumps at it, or if you like flip on a switch and you have a sudden event like that, you can't take the derivative of it because the rate of change doesn't really make sense in that context.
Well, sometimes you just can't take the derivative because, for example, if you were to like have something happen in a simulation, right, and you like wrote the code for simulation, you can theoretically make that simulation differentiable. But say, for example, your model is directly learning the real world. It is a robot arm in the real world that's trying to pick up a cup, and it fails to pick up a cup. You have a camera that goes, oh, it failed to pick up a cup. How do you backpropagate through the real world? You can't. This is air. There's no matrices happening here. You can't backpropagate through the real world. And especially with like self-driving cars, especially when you start to take it onto the streets and you give it like human feedback by say the car starts steering one way, you're like, oh no, don't do that, you steer it back. Those are feedback that you're getting to the model that can be turned to rewards, right? So these things you can't backpropagate through it because it's the real world. So we can't just use backpropagation in the sense. It's as simply.
Yeah. So instead, what we're gonna do is we're going to have a different function that will inform us how we need to update the model parameters. And that function in question is, okay, this thing. So if we look at this part of it, what we're trying to do is we're trying to maximize the expected value of our reward function. So this is an expected value operator, and this would be our reward function. And the way that we calculate that is with this integral, where we take the integral over the value of a reward function times the probability of entering that particular parameter for the reward function. And if we evaluate for if we integrate across all of tau, then that gives us our expected value. But the important thing to keep in mind here is the expected value. So if you want to maximize that expected value, we figure that out with this giant derivation. So the detail of the derivation, I guess, aren't strictly relevant necessarily, but just know that if we have some sort of state that we're in, right, and we want to maximize the reward function with respect to that state, then that ends up being this equation here. And this equation is something that we can actually calculate moment to moment as we go from state to state to state. And if you like look at this slide and like work through the math, it would be helpful to understanding it, but we're a little bit short on time. So I'm just gonna say that maximizing the expected value of a reward function boils down to this expression. Okay, so now that we have our component parts, then we can start doing our reinforcement learning, right? So what we'll do is, given some sort of state and given some sort of observation, we have some possible actions. We're going to sample some random action, or not random, but like according to our policy, we're going to pick an action. And then based on that action, we will end up going into, we will change our reward function somehow. And then based on how we've changed our reward function, we know that we need to update our model parameters here as represented by theta. And this alpha here is the learning rate, which should be familiar to you all from previous lectures. And this bit here is the change that we make to our model, the update that we make to our model. So it's the partial derivative of this expected value of a reward function with respect to all of the possible states. And that's how you update the value. That's how you update the parameters that control what our policy will be. Okay. So does anyone have any questions about what we've gone over so far? Okay. Now then, real quick, there are still some problems with reinforcement learning. So there are like 3 or 4 problems that we're going to talk about today. So first is training instability. So our reinforcement learning algorithms often require a lot of data. And also, because of this, they're very, very sensitive to the choice of hyperparameters, especially in comparison to supervised learning. And another quite frequent issue is that if we've trained our model to sort of imitate like human behavior, so if we're driving, then our model will learn to imitate human driving. But then what if the model makes a mistake and then it encounters a situation that it's never seen a human be in before, right? In that case, our model won't know what to do and it'll probably just do something random. But that something random will take it even further away from what it's learned. And so even the slightest deviation from the human patterns that it's learned is going to result in massive deviation over time. And so we're going to see that leads to unstable behavior. Okay. Second thing, reward specification. This is a huge problem, which is that I've been talking about a reward function, but someone needs to determine what that reward function is. And if they're not careful about that reward function, you are going to find that your model does really, really weird things. So for example, this is a game that the model has learned to play. So this is a race that the model is supposed to be winning. And if we observe what this boat is doing, you can see that the boat is just going in circles. And the reason for this is that the reward function rewards the boat for going forward, but it doesn't penalize the boat for going backwards. And so if you want to really maximize the reward function, right, you're not going to get to the end of the race because then that's a finite reward. But if you keep going in circles and you go forward, then backwards, then forwards, then not backwards. And that's a much higher reward. And so you see that this is what the boat is doing. It's maximizing its reward function.
Another thing is I think it's giving the boat like has it go like coins along the way, and there's like a bunch of coins there, and the boat's kind of circling it to get a bunch of coins, and it gets a bunch of rewards from that. But it's failing because the reward not as well designed for us to prioritize. Hey, you gotta get to the end, and you gotta progress in the course. The boat's just kind of spinning.
So that's a really big problem, right? And you can imagine how this is a pretty innocent example, but if you have a real world system and you don't specify the reward well enough, that could lead to some really catastrophic problems because we think the model's doing one thing, but it's actually optimizing for something completely else, something completely wrong that we don't actually want it to optimize for, but that we've told it because we didn't make our reward function good enough. And then, uh-oh, is it not? No. What? Hold on. Ah, there we go. And then next up, exploration. So typically, if we want our model to do really well, right, we want it to be exposed to a lot of unique situations. Because if the model is exposed to unique situations, it's going to learn how to deal with those better, and then it's going to be more effective overall. But the problem is, we don't want it to be too curious, because it might end up in a place where it gets exposed to a lot of information, but it doesn't actually, it's not useful information. So it's spending too long staring at something new without actually doing the task that we're trying to train it to do. And you can see that here, where something is trained to go through a maze, but then it sees like a screen that like is flashing a bunch of images, and it just gets mesmerized by the screen, and it just like stares at it indefinitely. Which, I mean, is not that far off from human behavior, I guess. But it's also not ideal as far as, model behavior.
More specifically, I believe this is an attempt to basically make it so that you're rewarding exploration in some way, right? Because like as we've talked about, if your agent comes up with a policy that is good enough, it will have a hard time actually going off and generalizing, but then also looking at new potential routes. And this is an attempt where it's based off of like all the input that it's getting, if it's experiencing something new and novel, you are also getting a reward. But as you can see here, it's kind of like taking away from it because it's just watching TV, because it's seeing a bunch of like new images and you know, I don't know, something TikTok like
Yes. Okay.
Yeah.
And-
Oh yeah, and right before we go to LMs, I want to give credits to those slides to John Dang, who is the XX ACM, yes, 3X's, 3XXX ACM president, who's still here at UCLA, by the way, graduating this quarter. This is actually our week 2 reading group. He's actually speaking. He's grad student. He's cracked, but like you know, like that was his week 2 reading group slides or parts of it. So if you want to learn more about reinforcement learning, that talk was amazing. You can find a recording of that on YouTube as well.
Yes, and then you can also, his slides go into a lot more of the math. So if you're interested in that, check out his slides.
Yeah.
And now I'll hand off to our team to go over elements.
Okay. The landscape of large language models. Okay. Overview. Okay. Transformers last time. Attention is all you need. Recap. Transformers were introduced in 2017 and they allowed for training in parallel, and they fixed the limited memory of RNNs, and they allowed for long range dependency because RNNs like forgot things as you went along and encoded. Again, we're giving a pretty high level because it's kind of like this survey. The original paper was like translation. So you got an encoder which encoded a sentence, got a representation, and then you had a decoder which used that representation to decode the sentence of another language. But as it happens, a lot of actual applications of these transformers were only used an encoder or a decoder. They didn't really use an encoder and decoder architecture, which was the original transformer paper. So what we're going to talk about first is BERT. BERT is bidirectional encoder representation from transformers. It's just the transformer encoder. I don't know why the naming was very, it's a transformer encoder. So again, this is what it looks like, yada, yada. It's just encoder. It just encodes. That's it. Okay, very simple. So what does an encoder do? Again, it encodes. Simple, I know, but it's like just abstract it away what it is. It's just the part that, encodes. Okay. Well, let's say we have this like sentence, like help Prince Mayuku, right? We get our model, it does its good job of encoding, we get a vector, and from that vector, we can then predict, we can put a classifier on it, like a spam classifier, and it can tell us, is that spam or not? You know, okay, it looks like spam because they're asking some friends from some country, something like that. Like this process and idea of encoding and extracting features you've seen before. Jordan's slides, for example, you have an image, you encode it, and then from that encoding, you can predict classes, right? Same concept of, again, encoding, getting a representation of, in this case, a representation of an image, and then you can classify it. Here we're doing a representation of a sentence, and then we're classifying as spam, not spam. But again, you can do other things like, is this happy, is it sad, other classifications, right?
And technically, the image classifier is really just an encoder with a very small classifier at the end, but we're just training it together. You can think of it that way as well.
Yeah. So, I mean, can it do anything? Can BERT do anything with size classification? Well, so far, if you actually looked at this diagram, we've only used the encoding of one single token. And if you remember from transformers, what we actually were doing was encoding every single token. So instead of just ignoring the other embeddings and encodings, so once we use the rest of them, this is used for attacks called sequence tagging. So you have a sentence, right? And what it does is it pretty much gets every word and labels it as, or person, whatever data. This is pretty useful for a lot of systems. But instead of doing this thing where we just grab this one representation, which is again encoding the entire representation of the sentence and classifying, what we want to do again is just grab each word and embedding or encoding, and then apply that dense layer to predict classes on words. So BERT can do more than just classifying a sentence. Specifically, this is called named entity recognition. So how do they learn to actually do this kind of encoding and get this really rich representation that we can do this classification with one single linear layer on? Like that's a pretty powerful thing that this can do. very simply, language modeling, like, again, very kind of scary. What does that mean? Large language models. It's just predicting a word based off the context of other words. So like the blank sat on the map. What is the blank? Anybody? Cat. So that's all the language model does. It predicts, okay, cat probably 50% of the time, maybe dog 20%. This is how language models learn. This is how we teach them to get representations and encoding. So if we look here, we give it the sentence like, let's, well, that's really like, sorry, but let's, whatever the sentence is, let's pick to blank in this skit. I think that's what it says, right? We literally, to train BERT, we just mask out one of the words. What we do is literally like, this was an embedding, like this is a vector embedding, vector embedding, vector embedding. We just like turn this to like 0 or some mask embedding. You just turn it to nothing, right? And what we say is when you encode this vector, pass it to the model, the encoding, right, should be rich enough as it's captured the context from the rest of the sentence that it can predict the missing word. And that's what you did when you said the blank sat on the map. You encoded this blank into a representation of the from the other words. You inferred what that word was from the context of the rest. That's exactly what what transformers do, is that you have this blank. The only way for it to do the task of predicting that blank word is by actually absorbing the context into the encoding of this blank representation, right? And from that, right, you have it so any of these encodings is going to be a really rich representation that not just represents the word that was there, but also its context in relation to the other words. By training it through this task of just given these words, what's the most likely word to be in the blank? That's how BERT is trained. Last training detail, they also, for BERT, they have 2 sentences, and then they also have the classifier, this little random other encoding, and they say, hey, does it follow the other one, right? So they do 2 tasks. So a real quick summary for bidirectional. Like they can look in both directions, like this word can look at the word, this mask can look at the words to the right and the left. So, I mean, that's just encoders. It's an encoder, it's a transformer encoder. Representation, again, it's a encoder again, like, I don't know why the name is so lengthy. And it's a transformer. Yeah, like bidirectional encoder for transformer. I don't know why they named it so long. It's a transformer encoder. So again, how is it trained? It's trained with mass language modeling. Again, we predict the blank, right? AKA fill in the blank. And the other task is next sentence prediction, where we say, hey, does the sentence follow this one? Right? And this is again not technical detail, it just gives it better learning capabilities. It gives us another task besides fill in the blank. So that's BERT. BERT was actually deployed in 2019. This helped a lot with search. Same with the transformers. Transformers was actually made by Google, right? Yeah. And then if you use Google Translate before that, it was like actually like so bad. But then like it translated word by word by word directly. But after this, they employed that in Translate. It was really good. And then 2019, they used BERT, which is again just this encoder, and it actually improved Google search a lot. So like, for example, here it says, can you get medicine for someone pharmacy? And then like Google is like, well, it said pharmacy and medicine, so I'm going to use some medicine link. But BERT actually was able to capture rich representation and encoding of it, of that sentence right there. And it then allowed Google search to recognize, oh, you wanted for someone. So look, the result is now, can a patient have a family or friend pick up the prescription, right? This was introduced in 2019, and as people said, it's probably the biggest leap in search engine history, right? It was in employing large language models to understand natural language and encoding. So BERT, very cool, still used for a lot of things today. 2019. Okay, GPT and OpenAI. So these are the big boys. This is even simpler than that whole BERT thing. It's even more basic and like, yeah. So these are GPTs again. Instead of encoders, they're decoders. They're the decoding part. That's it. BERT is encoder, GPTs are decoders, right? What does that mean? Okay, again, they read from left to right. Again, ignore that. Instead of predicting the blank, you say the cat is chasing the next word. Again, you can pretend there's a blank there, but again, it's not in the middle. It's given these words, what's the next one, right? And that's the difference. That's what a decoder does. So again, the cat is chasing the probably mouse, right? Could be these other ones. Same thing. The blank is the next word that we're predicting. This is what transformer decoders do. Yeah, catching the next word. Again, what these are good at that the encoders can't do is decoders are really good for generate, because what we can do is we can do robots must obey, right? Given this, what's the next word? Predict it, and we can append this to the end, and then robots must obey orders, and then we can predict the next word. So we can generate new text, and that's what you see in the GPT. It's a transformer decoder. Again, the encoder can only get a representation of the sentence that you have so far, really rich extract features, but a decoder allows you to actually generate, right? That's the real power of the transformer decoder side. So again, recap. You have encoders, decoders, attribute translation, that's all we really said there. You have encoders, which we did sentence transformation, name entity recognition, we did that. Again, it's mass language modeling. And then the decoder, which is text generation, right? So this is kind of like some brief overview of like how they're used and when they're used. But again, this is translation, this is BERT, BERT's there, yeah. And then look, this is GPT, right? So here comes GPT-3. This is June 2020. So just a little reference. This is our BERT. This is what we're talking about. When we say BERT, this is 340 million parameters. That's what BERT is right here. This is what is employed in Google search that we talked about, used for all those cool things, embeddings, right? This is an encoder. GPT-2, right, which came out, I said there, that was GPT-2 we're talking about here, by the way, 2019, right? So GPT-2 is 1.5 billion parameters. Crazy, 2019. Oh my gosh, that's crazy. Who's going to build anything bigger, right? Boom. June 2020, they trained a 175 billion parameter model. That is insane. Google, like, this is like such a good encoder and representation. And GPT-2 with generate text, and we have these other two, which are other ones we can ignore. Like 175 billion. Let's just like break that down real fast, okay? Where is it? Oh. $4 million. They spent $4 million on compute. Imagine running your computer, right? It's like takes electricity. It's like, okay, that costs $4 million. How do you even do? I don't know. Like, I don't know how my electricity bill get that high. That's insane. That is an insane amount of money. And look how much data they use. 560 gigabytes of text. Do you know how small text files are? Have you written a file that's even like a megabyte? Text file, 560 gigabytes of, like, this is just massive numbers. And this is how OpenAI, this is the approach they have. They just throw massive amount of money, $4 million, just so much data, and they believe that it will scale. And it worked, right? Again, this is a breakdown. The actual data is just straight from there. This is just websites. Decent amount of Reddit. That's interesting. Yeah, probably not. That's why.
If you have noticed that ChatGPT used to, like, it is, at least before, it used to be very confidently right, very confidently wrong about certain things. It's because part of the reason people speculate is because they use a lot of data from Reddit. Anyway.
Yeah. So again, the results. Oh my God, this is mind-blowing. Like this, like now it's so lost on. I feel like all of us, but like 2020 is like crazy. You saw them like type in, make a button with this code, and it just made the code, and you're like, oh my. Now it's like we don't even care.
And for reference, this is around the time when the first diffusion models came. They're like, oh, we can generate pictures of faces.
Yeah.
And all the like in natural language modeling, they were doing this. So it's like this was insane, especially still now, but especially at the time.
Yeah. And this is my high school AP Gov assignment. So I showed this in the GPT, and I gave it 2 examples. Literally, this time is so funny. They literally had 2 examples, and they want me to do it for every election from 1936. That was insane, right? Wow, really good. It's really good at that pattern recognition, and everyone was blown away. This is 2020. It was writing things. It was doing amazing, right? So where did it fail? If you were one of the users using the playground in 2020, what you might have realized is that you kind of have to prompt it pretty well. Like if you just ask it, explain the moon landing, it would go like explain, and like what? Why is it doing this? Again, it was not great. Another example, what is the purpose of code? I gave it some, like I asked it a question, and then you give it some code, and then it like outputted like A, B, C, D. Like what? I want to know the answer. Again, this kind of makes sense though. It was trained on predicting the next word of text on the internet. The internet is not going to have instructions and then really nice correct answers following it. It's going to have this very random variation in structured data. So you're going to see patterns where you're gonna see probably this makes kind of sense. You're gonna have a question, and then you have it, and you're gonna have a bunch of multiple choice answers. That's probably what's more available on the internet than a question and a very precise, correct answer and explanation, you know? And again, there it's like, again, pattern recognition, all that stuff. So it kind of makes sense why it's bad. But what we realize is that, well, I've been saying shots or examples, right? What's called zero shot is when you just give a no example. You say, hey, translate into French this word cheese, and then go, right? And it's not that good at that. Like I just showed you, like if you say explain this, it's going to explain, giving the answer. But if you give it, for example, what's called one shot, one example, you say translate English French. The other is this, the cheese, what would it be, right? Instead of just giving cheese, if you give it one example, just one example, its improvement goes from 10% to almost 50 accuracy on any prompt that people evaluate, right? Which is insane. So it kind of showed us that these things are really smart, but like they are really dumb in some other ways, in that they just don't know how to respond. It's imagine like a person who's seen everything and then they're like, what are you asking me? You know what I mean? So that was the real problem with GPT in 2020. So then again, shots, the few shot, right? Takeaway, model performance increases dramatically when just giving like one example, right? And you can see it kind of tapers off when you give more and more examples. But again, just one, like look, 0 examples, and you give it, hey, this is what I want. This is the pattern you want to see. Because once it sees the pattern, it's like, oh, I can do that again, right? Again, internet, unstructured data. So how do we, why is this? Again, the GPT name, the GPT-3 paper name that they spent all the money on is language models are few shot learners, not language models are 0 shot learners, right? They're really, really good when you get them few shot, but 0 shot, nothing, right? So here comes, well, what if GPT-3 could be a good 0 shot learner? This is the Instruct GPT paper. This is pretty much up till now, this is ChatGPT. This is how it's so good at responding. It's called Instruct GPT, yeah. So Instruct GPT, this is 2022. So this is literally, I think, a month or a couple months after this, ChatGPT blew up and then it went crazy. I think the timeline is there. But remember this example, explain the movie in a 6-year-old, explain that, it's kind of like repeat. This is like so annoying. You always have to prompt it. I hate that, right? Boom, instruct. What you're used to now, okay? But like still, like when that came out, you're like, ChatGPT, what? How are they doing this? Like it makes no sense. It's just unstructured data from the internet. How could we ever get it this good? Well, again, another example. It actually does it. It doesn't give you like a list. It explains it to you, which again we're used to. But like imagine when this paper came out, we're like, oh my gosh, what? Okay, so how does it get these insane results, right? These are really good. How did you get it to do well? And again, from the name, instruct. How do you get it to listen to instructions well? All you do pretty much is you just get humans responding to data really well. And then you just fine tune it on the next word on that more. That's pretty much the underlying thing. So you just get like example, it's like a 6-year-old. You get a human, like a person, you to like write a good response, and then you just have the high quality pairs of instructions responses. You have text, literally instruction, human really good response, and then you just have a new data set of that, and you just train it on that, and that's it. You just train on people writing good responses. And again, the whole point is that it's really smart. The model is, again, as we showed, it's really good, but you just need to give a few examples. And if you just show it how to respond well, it has the capability to do really well, and it learns, oh, this is how a good response is, right? So that this fine-tuning process where we're grabbing human written stuff, it's not really teaching it anything else. It knows everything. It's just teaching it like how to act, right? How to respond to a prompt, right? That's kind of the general intuition. Yeah, OpenAI used 10 million workers and paid them less than $2 an hour to get these responses. That's like, yeah, that's a thing that happened. Just putting that out there. Anyways, let's look at results. So this is like 0 shot, right? You ask it, hey, explain me to a 6-year-old. And then here, you're like, give it a couple examples. I think it was like 3 or something. Give them 3 examples, right? And look how much better it does. This is a score of human preferences 1 to 7. So humans literally just rated responses. That's how they do it. And then this is a supervised fine-tuning thing where we train it on examples. And even if you give examples, like you gave original GPT, just a bunch of in-context examples, like you did multi-shot or few-shot, if you supervise fine-tune, it's even better, no matter what. And what's really interesting from this to see is that they trained multiple models. They trained 1.5 billion. This is like our GPT-2 exercise, right? Remember that? And then this is our big one, 175. What they showed is that the GPT-3, the 175 billion parameter model, humans didn't like it more than a GPT-2 with this fine-tuning supervised two process, right? That's what they showed. So again, it kind of makes sense. Like, I don't care if it isn't super smart. If it responds like this, I don't care. You know what I mean? Again, the few shot example was different, but again, that initial response is what we really care about. Zero shot, no examples. I'm telling you, do the thing I want, right? And it showed how much better you need to do this, right? It doesn't even matter if it's smarter. Again, you can see that once it's smarter, once it's in the smarter range, it does help it a little bit, but it really is about getting it to do what we want. So there's a second step they did though, not just this supervised fine tuning. This is a little more, but this is called reinforcement learning from human feedback, right? So this is step 2 and 3 of the Instruct GPT paper. So they did fine tuning. Then, okay. They get GPT. Here, I'll just read it from here. Yeah. So they sample a random prompt, right? And say GPT generate a bunch of responses, like explain the moving a signal. Okay, generate response, generate response, generate response. You have the GPT generates 4 responses for you, let's say. And then they have a human rank the responses. I think this one's better, I think this one's worse, right? We use that to train a model that learns human preferences. So it learns, okay, given these 4, how should I rank them, right? It learns from humans ranking, it learns how it should rank them, right? So you get a model. This is a separate model. This is like maybe a 1.5 billion parameter GPT or some small language model to learn human preferences. Then from there, we have GPT generate a text again. We have it then, I give it a prompt, we have a generated response, and then we have the reward model we just trained on human preferences evaluated, say, how good was that? And we use that as a signal, right? And this worked. This is extremely better than even supervised fine tuning. Why that is? I think the intuition is kind of like, if we're giving it data and we're just saying, here's something good, here's the right response, here's like general respond with, it might just kind of tunnel vision, right? Whereas when we do this kind of thing where we let it generate just a giant breadth of responses and we can rank them, it kind of lets it in a way like when it generates a response, in the original case, if it isn't exactly what we wrote, it's not going to learn to do behavior like that. But in this case, since we're training a model to learn just the general preferences, if it generated something that isn't exactly like what we would write, but it's decently close, it still gets a reward signal. That's kind of an intuition, I guess, you can get from that. But yeah, way better. So this is kind of the levels. You just pre-train, I'll go through the process real fast. So you pre-train on the internet, just enormous amounts of data, predict next word. You then have humans write good responses to instructions, train on that a little further so it gets good. And then you do this process where you get humans to rank them. You train a model to learn that kind of ranking. And then you use that in a reinforcement learning process to have as a reward signal to its output. So you train that further, right? So again, this is it's pre-trained off the internet. It's pretty bad. It's going to be garbage. It's garbage. You prompt it, okay, it's seeing the pattern. It's like, no, it knows what you want. You fine tune on good human data. And then finally, you do this reward modeling feedback loop signal, right? And this is how it works today. ChatGPT works today. And a lot of research is on that last process right here of that reward signaling and getting it to align. Because a lot of times, as you see, that's really what we care about. Again, these models are good at multi-shot referencing and like if you get a bunch of examples, but what we care about, this graph really shows what we care about. This is like humans sitting there and rating them. So this area of research is really big, right? This RLHF, reinforcement learning, to do that. Big thing. So yeah, large language models right now. OpenAI's ChatGPT, if you look at Meta, they have Llama 2. If you have to look at it, I think they say this has 100,000 supervised fine tuning. So this is what we're talking about, where we just give examples. And then this is 1 million preferences. So this is 1 million humans went, or there's 1 million, here are the generations and let me score them, right? So they actually release data. And what's nice about Meta is only company to release the monoliths. You can download these and run this on your laptop and fine tune it more and do whatever. OpenAI through an API. Google Bard runs on what's called Palm 2. So yeah, that's kind of it. Here's a little diagram. Go and break it down. Your GPTs run ChatGPT. Palm is Bard, Claude, and then Llama is we love Llama. Any questions about anything? That's kind of, I think that's it. Yeah, that's the end of it.
That's all LLMs, that's it, no more LLMs.
No more. We pause. Yeah.
Yeah.
Any question? Any confusions? Encoders, decoders, this process, the data. No. Okay. I think we're good. Yeah. Last slide.
Yeah, last slide, yeah. Okay, yeah, that's the last slide. Yes, okay, thank you for coming to Advanced Track. All of y'all will get the Advanced Track and start to finish. Stop back. Thank you so much.